now in this second part, we are going to start talking about waveforms and the parameters of electrical stim. So for the learning objectives, and these are listed in the module, of course, I need you to be able to define/describe all the waveforms discussed in this lecture. So the three main waveforms that we're going to talk about, and we're going to continue to talk about throughout this module and next module, are direct current, alternating current, and pulsatile current. And we'll define and describe what those three all are. The parameters for all those different currents that you should know are amplitude, pulse duration, phase duration, frequency, duty cycle, rise time, and ramp time. And we'll talk about all those. We want to know how eStim can generate an action potential. So we talked a little bit about action potential last time. Physiologically, they're generated from a nerve impulse from the brain or some other part of the nervous system. But now we're going to do it artificially with electrical stim. So, furthermore, how does eStim stimulate a motory, sensory, or noxious pain nerve in terms of amplitude and duration? So what determines whether a sensory, motor, or noxious response is elicited with eStim? And the hint here is that we're going to look at the strength duration curve. So this is a graph that you should be well familiar with by the end of this module. And you should be able to draw it out and explain it and its application to eStim, because this is one of the key concepts that we need to understand is what's the difference? How do we stimulate those different nerves? We should also know how frequency influences the treatment. We'll talk about frequency and how it influences the treatment. So in the lab, one of the first things we'll do is we will plot our own strength duration curve. So we're going to see how amplitude and duration influence what we're feeling. So you're going to plot your own strength duration curve using an electrical stimulator unit. So a waveform is a shape or visual representation of an electrical current. So these are all just examples of waveforms. The ones that we usually see in clinical use in electrical stims are the one on the top left and bottom right, the sine wave and the square wave. The triangular wave and the complex wave might be applicable in some other non-therapeutic setting. They're still waveforms, but they're not used therapeutically. The sine wave and the square wave are more commonly seen, and we'll talk about them. So the actual waveform that enters the patient depends on the resistive properties of the tissues, and that's going to alter the shape of the waveform. But are we able to see that or measure that? No, we are not. So we know how it is going in. We know the clinical and therapeutic effects that it has, and that's what we need to know. So the three types of current, three main waveforms that we're going to talk about are direct current, alternating current, and pulsed current or pulsatile current. So all of the applications that we use in eStim use these three types of waveforms. Okay? So direct current is where it's a continuous unidirectional flow of charged particles. So the electrons flow in one direction for at least 1 second. There are two electrodes. One is positive, the anode. The other is negative, the cathode. It's continuous. It's flowing for more than 1 second. The current flow is dependent on the polarity set on the machine. So that's something that we set. We decide where we want the electrons to go to and from, and we set that, or it's set on the machine. Direct current is most often used clinically for iontophoresis, which is the transfer of transdermal medication, or medication through the skin, across the skin. There is a net charge, meaning there is an accumulation of ions underneath the electrodes, so there's more of a potential for side effects with iontophoresis. So the other applications that we use besides direct current have no net charge, so there's no accumulation of ions. Because we're moving the electrodes from one place to another, or the electrons, excuse me, and we're driving them with the electricity, we're sort of herding them into one direction, we get accumulation of electrons in one area. So the reason we do that for iontophoresis is because the medication is a charged ion that's dissolved in a fluid, and we're driving it into the skin. So we're trying to move it from one place to another. Alternating current is a continuous sinusoidal bidirectional flow of charged particles. Alternating current has equal ion flow in each direction, so there's no net charge within the tissues. So the current changes direction of flow at least once a second, so that the rapidity with which it changes direction is the frequency. So each little blurb above and below the 0 on this graph is a change. So you can see that all the above, because it's a sinusoidal wave, each wave is equal. So the amount of charge above the line and below the line is equal, so we have no net charge. So alternating current can be ongoing, where you just have on, off, or positive, negative. That's why they call it alternating. Or you can have bursts. So there's an interval in between a burst of alternating current. We'll talk more about that. The alternating current, an alternating current of adequate frequency and intensity can produce a muscle contraction, a tetanic muscle contraction. Tetany is when we get that strong, full muscle contraction. You can also stimulate sensory nerves with it. So with all of these different current forms, you can stimulate motor or sensory nerves. So AC is the continuous, uninterrupted bidirectional flow of particles. The polarity continually reverses between electrodes, and there's no net chemical buildup in tissues due to the changing current. So no net charge. Pulsed currents, they consist of an interrupted flow of charged particles, whereby the current flows in a series of pulses separated by periods when no current flows. It's also called pulsatile current. So a pulse is comprised of one or more phases. So each phase is either the positive or negative charge, so the part on the waveform above or below the line. A monophasic current, each pulse has one phase. So in that upper graph, graph A, that is monophasic current. So it's positive, 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 with spaces in between. In a biphasic current, each pulse has two phases, positive, negative, space, positive, negative, space. So that's that lower curve. It can be a unidirectional or a bidirectional flow of charged particles. So we said direct current was unidirectional. Pulse current can be either unidirectional or bidirectional. There are periodic interruptions in the current flow. Those are the pulses, is when we have, or the space in between the pulses. It's a common type of current used in electrical stim applications. So you can see that in the biphasic current, there's no net buildup of charge. In a monophasic current, you could have a buildup of charge. So in monophasic, the current flows in one direction. There's a defined anode and cathode, just like in direct current. The only difference between direct current and monophasic pulse current is it's not continuously on in pulse current. It's on and off. In biphasic, the current changes direction once in each pulse. So each pulse contains two phases, positive, negative. So you have no net charge. So you could have a higher positive pulse phase and a lower negative phase, and then it's asymmetrical or unbalanced. Let's just say all of the therapeutic applications, it's a symmetrical balanced charge. So just like alternating current, pulsed current of sufficient frequency and intensity can produce sensory and or motor excitation. So that's what we're trying to do with electrical stim, is we're trying to stimulate sensory or motor nerves to get a therapeutic effect. So alternating current can do it, pulsed current can do it. So amplitude is the magnitude of current or voltage. So when you're turning up the power, you're turning up the amplitude. The current is required to flow to have the cell reach its threshold and generate an action potential. So you do that by turning up the amplitude to get to the level where you create an action potential. The rise and decay time. So the rise time is the time for the phase to go from 0 to peak, and the decay time is to go from peak to 0. This is sub-sensory. So in other words, you cannot detect the rise and the decay time. The rise time, or the rate of rise, happens over micro, so 1/1,000,000th of a second or 1,000th of a second. So it's below our level to sense that. We just can't sense that short amount of time. But a rapid rise time will overcome the excitable cell's tendency to accommodate. It's important when stimulating nerve cells to have a rapid rise. So this shouldn't be confused with ramp time. We'll talk about ramp time in a minute. But the rise and decay time is built into the device. The ramp time we can adjust. The rise and decay time is undetectable by human senses. The ramp time is detectable. Okay? So when we're talking about pulse or phase duration, the pulse or phase duration is the time in milliseconds or microseconds that a given current amplitude has to flow to have the cell reach its threshold and generate an action potential. So the phase duration is the time from the beginning to the end of one phase of a pulse. So it's marked out on the graphs here. You can see the phase duration. The pulse duration is the time between the beginning and the ending phases of the pulse, including the interpulse interval, which is the time between pulses. So basically we're just specifying the different parts of the curve, if that makes sense. So the pulse duration is the time during which, the phase duration, is the time during which the current flows in one direction. The pulse duration is the sum of all phase durations and any intervals within the pulse. So pulse duration is particularly important when we're going to determine what is an adequate stimulus for direct muscle stimulation for muscle that isn't innervated. Deinnervated muscle requires a really long pulse duration. Innervated muscle will respond to a pulse duration of 300 microseconds, but deinnervated muscle needs milliseconds, so 3 orders of magnitude different. So when we look at this chart, this is the strength duration curve, and you can see that along the y-axis we have current strength in milliamps. That's the amplitude. Along the x-axis we have pulse duration in microseconds or milliseconds. So it's amplitude on the y-axis and time that the pulse is on the x-axis. So if you look with these lower pulse durations, we're going to stimulate the A-beta sensory nerves. Okay? And remember when we talked about pain, those A-beta nerves, they're important with a gating effect to block those pain sensations at the spinal cord level. So we want to stimulate those A beta sensory nerves. We need to keep our pulse durations below 100 microseconds. Okay, you can kind of see that on the graph. So once we get up to 100, we're going to start stimulating some motor nerves. So when you put the electrical stim on and you start to turn up either the duration or the amplitude, you get to a sufficient amplitude, you are probably going to start stimulating motor nerves anyway, as long as you have a long enough pulse duration. So it's the combination of amplitude and pulse duration that's going to determine which nerves you stimulate. So you can see this. We have the A beta nerves, the motor nerves, the A delta, which is the sharp pain nerve, and those are all at pretty short pulse durations. When we get out to the C fibers, which are the dull pain and denervated muscles, you need a longer pulse duration to stimulate those guys. So basically, what we're trying to do when we're trying to stimulate a motor nerve is we're trying to get the combination of duration that we get a motor response and amplitude that we don't get a sharp pain response. So it's a fine line, and it's also personal. So in lab, when we plot our own personal strength duration curves, everybody's is going to be a little bit different. So we're not dealing with machines here, we're dealing with human beings. And so everybody's sensation is going to be different. So one person's sensory response is going to be different from another. So current has to flow at an adequate intensity and duration in order to depolarize a nerve cell, causing it to reach threshold and generate an action potential. So current flowing during a given pulse or phase duration, when we think of it all together, it's the charge. It's the pulse or phase charge. That's in coulombs. We talked about that in the last lecture. Charge is the key to excitation. So we have to have a sufficient intensity and duration in order to depolarize either those A beta cells, the motor cells, or getting into the sharp pain thing, the A deltas. Charge is the stimulus for neuromotor excitation, whether it's sensory nerves or motor nerves. Okay? So we're going to get that combination of amplitude and duration that's going to stimulate the nerves that we want to affect. So if both phases of a biphasic waveform give you the same charge, then there's no net charge component. No charge will accumulate under one electrode or the other. And that's what we want. We don't want accumulation of charge, except in direct current. This feature is sometimes called the zero net charge component, and it protects our tissue from charge accumulation and burns. So having a burn is the potential side effect of the buildup of charge underneath an electrode. And there are different reasons why that might happen, and we'll talk about them. So the frequency is the rate. So it's how many pulses in pulsatile current or how many cycles in alternating current per second. It's expressed as pulses per second, PPS, or hertz, which is cycles per second. So the definition of a hertz is 1 cycle per second. So it's basically how rapidly the waveform repeats itself in a given time period. And it relates to the refractory periods of the nerve cells. So frequency is not duty cycle on-off time. Frequency is how many pulses per second or alternating current cycles per second. On-off time is important for controlling fatigue during muscle strengthening treatments. So the on time is when the electricity is flowing. The off time is when it is not flowing. So during the on time, you might have lots of pulses, so you might have a certain rate, frequency. During the off time, you have no pulses or no cycles. So on is electricity's on, off is electricity's off. So with alternating current, frequency and pulse duration are tied to one another in an inversely proportional relationship. So if you have a higher frequency, you're going to have a lower pulse duration. If you have a lower frequency, you're going to have a longer pulse duration. So this picture from the book kind of shows you that, because if you have a lower frequency, there's more time before it switches, so you have a longer pulse duration. In pulsatile current, the frequency and pulse durations are independent of each other because the pulse duration is regulated independently of the frequency. So the pulse duration is usually in milliseconds or microseconds, and there are variable interpulse intervals. So that's really kind of the main difference between alternating current frequency and pulse duration and pulse current frequency and pulse duration. In alternating current, you're going to set the frequency and the pulse duration is going to figure itself out. In pulse current, you're going to set the pulse duration, and the frequency is pretty much going to figure itself out, even though you can set it too. So it just has to do with which parameters are adjustable and which aren't, and we're going to talk about that with regard to specific applications. So the duty cycle, that's that on time, off time. So when you have off time, the current is interrupted in real time. So you can feel on and off time. You cannot necessarily feel the pulse duration unless it's, or the pulse frequency, unless it's a really low frequency. If something's going at 50 cycles per second, you might not be able to feel each distinct one. If it's going at 10 cycles per second, you probably can feel each distinct one. So on-off time or duty cycle is usually used when you're stimulating motor responses to allow relaxation time for the muscle between contraction times. So it combats muscle fatigue during electrical stim. So the time on / time off, or time on : time off, is the duty cycle ratio. So if you have 1 second on and 2 seconds off, it's a 1-2 ratio. You can also express it as a percentage. So like 1 second on, 3 seconds total time is 33% duty cycle. So 1 second on, 2 seconds off. So it can be either expressed as a ratio or a percentage on off time. So ramp time, this is also mostly used with muscle stim. It's a gradual change in amplitude during a series of pulses or cycles. So ramp time is used so it doesn't just go on at its maximum. It's used to ease you into the muscle contraction and then ease you out of it. And ramp time is largely for patient comfort. A modulation is where you vary one or more electrical parameters to postpone adaptation or accommodation. So you're varying one of the parameters just so you don't get used to it as easily. So in alternating current and pulse current may be modulated. The amplitude, duration, or frequency, or any combination of those three, can be automatically varied in a predictable or a random fashion. And those are settings that you can set on the machine. So the idea of modulating is to provide a novel stimulus to the sensory or motor nerves so they continue to depolarize and generate action potentials and respond. So if you keep changing it up, the nerve doesn't accommodate as quickly. So it's basically an alternative to continuously turning up the amplitude, because as the nerve accommodates, if you don't modulate, you can keep turning up the amplitude to a point because you're going to get used to it. And this is usually used in pain modulation. So when we talk about specific pain applications, we will talk about this. So the graph from the book kind of shows amplitude modulation. The amplitude goes up and down in a predictable pattern, and you can set that on the machine. Frequency, it's slower and faster for the pulses or cycles per second. Duration, it's longer and shorter pulse durations. And again, it can be predictable or unpredictable. And that's just to prevent accommodation. That's the main reason for modulations, is to prevent you getting used to it and having to continuously turn up the amplitude because you got used to that level of stimulation. So with the ramp times, either the amplitude or duration can be increased gradually over seconds. Usually we're talking about 1 to 2 second ramp times, and then decreased gradually as well for the ramp down. So it's used to gradually recruit more motor fibers and to gradually increase the force of muscle contraction. So it's usually included with the on time part of the stimulation cycle. So if you have 10 seconds on, 30 seconds off, part of that 10 seconds on is going to be the ramp time. It's not to be confused with the rate of rise or decay time of a single pulse, which is undetectable. It occurs over milliseconds or microseconds. Ramped current is detectable from a sensory and motor standpoint because it occurs in real time over multiple seconds. So rise time and decay time occur in the shortest amount of time that's undetectable to us. Ramp time is detectable. You can feel the ramp time. So when an excitable muscle cell is depolarized frequently enough to reach its critical fusion frequency, meaning the muscle is, all of the twitching fuses into one tetanic contraction, that is the most functional type of muscle contraction. It usually happens between 25 to 75 pulses per second or cycles per second. You might use higher frequencies to elicit a stronger contraction. And so we'll talk more about this in chapter 12, but the percent of the maximum voluntary isometric contraction, that's how we measure how strong the contraction is. So you can see in this chart that when we have lower frequency, lower pulses per second, we might get muscle twitching. That's that little jagged line. But then when we get to higher pulses per second, the twitches all join together. They fuse together into one strong muscle tetany, of one strong tetanic contraction. So if you have muscle twitching going on and you want tetany, you're going to turn up the frequency. So that's the answer to one of the learning objectives, how frequency affects muscle tetany. So if you're getting twitching and you want tetany, you're going to turn up the frequency. So all of these parameters apply, or most of these parameters apply in the different types of current. So in direct current, the current flows equally throughout the stimulation. So the only parameters you're going to adjust are amplitude and total treatment time. Because you don't have a pulse, there's no pulse duration. It's just on the whole time, and you don't have interpulse intervals. So you're going to adjust the amplitude and the total treatment time with direct current. With alternating and pulsed currents, there's pulse duration, phase duration, interpulse interval. You're also going to adjust amplitude, frequency, on-off time, and ramp up, ramp down time. So lots of parameters to adjust in alternating and pulse currents, not so many in direct current. Just 2, really. So the action potential, it's that basic unit of nerve conduction, and once the nerve depolarizes, reaches threshold, it's going to depolarize and propagate that action potential down the axon. Remember, we talked about that in the last lecture. So the stimulation of action potentials in nerves, or neuromuscular electrical stim, we call it, has to do with the strength duration curve. So basically, the strength duration curve talks about the amount of electricity required to produce an action potential depending on the type of nerve. So sensory nerves are going to be shorter pulse durations. Motor nerves are going to be longer pulse durations. I mean, that's really the upshot of the strength duration curve. Shorter pulses for sensory, longer pulses for motor. With electrical currents, when you have